We'll start now by looking at the simplest type of Doppler instrumentation, which is continuous wave Doppler. This is almost universally abbreviated as CW Doppler. The concept really is simple. There are two transducers, or in the case of a cardiac machine, the probe is divided into two halves. In either case, one transducer transmits continuously, and the other one receives ultrasound echoes continuously. So this is the one form of diagnostic ultrasound where pulses are not used, and we are in fact using continuous ultrasound. Naturally, the amplitude is low, so that the total energy delivered to the patient is within safe limits. So the machine receives echoes from the tissues and detects any Doppler shift, and it can then display that Doppler shift. Here we have examples of two handheld applications of CW Doppler. On the left, we have a unit that might be used in a vascular laboratory, and on the right, we have a fetal heart detector. At the other end of the scale, we have a very sophisticated echocardiography machine. This will also have continuous wave Doppler incorporated into it. The reason for this is that CW Doppler is able to detect extremely high velocities, such as occur in the heart when you have severe pathology. Later we'll see that pulsed Doppler is incapable of doing that. Here is the concept. I'm showing a handheld probe, and you can see the transmitting transducer and the receiving transducer angled a little so that their beams will overlap. Anything that lies within the overlap area between the two beams can contribute to the echo signal being received. So on the right-hand side, you can see that I've labeled this overlap area the sample volume. That's the region from which the machine will detect anything that is moving and will detect Doppler shifts from it. The only thing that limits this in depth is likely to be the attenuation of the ultrasound. This diagram is intended to give you an idea of the way the CW Doppler processes the echo signals. So in the top left, we have the transmitter sending a frequency F to the transmitting transducer. The Doppler shifted echoes, and I'm showing that as F plus FD, where FD is the Doppler shift, is then very weak, it's amplified, and then that amplified echo signal, still with the same frequency, F plus FD, is fed into a circuit called a detector. The detector has the property that it receives two different inputs and it detects the difference in frequency between them. So it is also given a sample of the transmit frequency F, and it can therefore detect the Doppler shift, and it discards the ultrasound frequency component. So if we have an ultrasound frequency of 5 megahertz and a Doppler shift of 1 kilohertz, the output of the detector is simply the 1 kilohertz frequency. So the detector is actually putting out the audible frequency, the audio frequency Doppler shift signal. That is then wall filtered, as I mentioned in the previous talk, to remove echoes that might come from moving tissues, and we then have an audible signal we can listen to, and that is also processed to produce the spectral display that I've shown you. One extra complexity which I haven't shown you here is that the machine processes the echo signal in a way that allows it to tell whether the blood or tissue is moving towards the probe or away from the probe. Here we have an example of a continuous wave Doppler acquisition in the heart. On the top, you can see a typical sector image of the heart, and a portion of that is being displayed with color Doppler. The sample volume has been steered approximately down the center of that color box. There is a dotted line there which you may be able to see, indicating exactly where the sample volume is steered. This then has acquired the signal that's displayed in the lower part of the image. Notice that it's below the line, indicating that it represents flow away from the probe. Notice also the negative signs on the vertical axis of the spectral display, again emphasizing the flow is away from the probe. Notice also that the vertical scale is calibrated in meters per second, not centimeters per second as we saw in the past. The reason is that this is an extremely high velocity. In fact, the peak velocity is around 3.5 meters per second, which is 350 centimeters per second. Now, two other things I'd like to point out here. One is that the Doppler sample volume will also be acquiring Doppler shifted signals from other parts of the heart where the velocities are lower. Those are going to be displayed mixed in with the signal of interest here. But because the velocity is lower, we're still able to see the signal of interest, which is the extreme high velocity one. So it doesn't matter that we are picking up interference from other parts of the heart. We can still trace and measure that high velocity signal from the valve. The other thing is that I placed a pair of green lines on the left-hand side around the baseline, indicating where the wall filter has removed the echo signal. So you'll notice that there's a dark band around the 0 Doppler shift baseline, and that's because that's where the wall filter has removed Doppler shift signal. So in summary, continuous wave Doppler is very simple. Handheld units can be very small, compact. You can just carry them in your pocket. But in addition, CW Doppler is also incorporated into very sophisticated echocardiography machines. It's not built into general purpose machines as a rule. The big disadvantage, if you like, of CW Doppler is the large, poorly defined sample volume. Now, for handheld measurements, this can be a convenience because it means that the positioning of the probe is not critical. But, of course, you're not able to selectively get the signal from a well-defined small volume. That's where pulse Doppler comes in, as we'll see. The big advantage of CW Doppler, and the reason that this simple technology is still around, is its ability to display and measure extremely high velocities that pulse Doppler and color Doppler can't cope with.